Okay, thank you everyone for attending my presentation. This is part of the UQ hybrid seminar that the chair of mathematics for uncertainty quantification is organizing. So the title of my presentation is Dynamic Splitting Method for Rare Event Simulation. And this is a joint work with Professor Zdravko Botev, Professor Mohammed Slim Malwini, and Professor Raoul Tamponi. So during my presentation, I will start briefly with the motivation and defining the main concepts that are very useful to in the development of our approach. Then we show how this classical splitting method cannot be applied to our setting, and we show how we modify it. In the third part, we show various applications of the proposed approach, and we focus mainly on applications from the performance analysis of wireless communication systems. In the fourth part, I will talk about two heuristics to determine the time where splitting is performed, and before concluding, some simulation results will be shown, and the comparison with some of the existing estimators will be presented. So in various applications, we often encounter the problem of efficiently estimating the statistics of sums of random variables, and particularly in the study of wireless communication systems. So as a first application is in the computation of outage probabilities. And by outage, we mean that the communication system does not work properly, and the operator needs to do something in order to correct this problem. The second application is again in the computation of outage probability, and assume that user transmit a signal to base station, but there are some interfering signals that come from different sources, and then this will deteriorate the signal to noise ratio, and this is again an outage probability problem. The third application is very recent in the field of free space optical communication. People start to communicate with laser, and sums of random variable is encountered to compute the probability of missed detection of pointing and alignment of free space optical communication systems. These are not the only applications where the sum of random variables appear. Other applications are in financial engineering and insurance risk. For example, the evaluation of the value at risk of a financial portfolio requires the statistics of sums of random variables. All of these applications and many other can be grouped into a single framework, which is the computation of probability that a quasi-monotone functional falls below a threshold. And we'll define in the next slide what is quasi-monotone function. So in a more abstract way, the aim of this work is to estimate rare event probability of the form in equation 1, where L is the probability that S, which is a functional from Rn to R, X is a random vector of independent random variables with cumulative distribution function Fi, and gamma is a fixed threshold. And by quasi-monotonicity, we mean the following. So we divide the index set 1 to n into two sets, I and D. And the importance function S is called quasi-monotone if when xi is less than yi, when I is in the set in the index set I, and xi is bigger than yi when I is in the index set D, then this implies that S of x is less than S of y. So many examples that satisfies the quasi-monotonicity. The first trivial one is the sum of x1 to xn, and this satisfies the quasi-monotonicity property with I equal to the full set, and D is the empty set. And the other example is the ratio of random variables, so x1 over x2 plus x3 up to xn, and we add another constant. And then this satisfies the quasi-monotonicity property with I is the index set 1 and D is the index set from 2 to n. So the standard approach to evaluate this probability is to use naive Monte Carlo estimator, and the estimator is given in equation 2. where the samples here are independently sampled according to the distribution of this random vector, where each component of the random vector is independently sampled according to FR. Next, if we compute the coefficient of variation of the naive Monte Carlo estimator. So the coefficient of variation is just the standard deviation of the estimator over the probability of interest. Then we find that this coefficient of variation is approximately equal to 1 over square root of L times M. And from the central limit theorem, the number of samples needed to meet 5% relative error should be selected approximately equal to 1,600 over L. So for example, if you want to compute or estimate the probability of order of 10 minus 8, then we need 16 times 10 to the power 10 samples in order to meet 5% relative error requirement. So this proves that naive Monte Carlo is not efficient in the regime of fair event, and one need to use other techniques from the family of variance reduction techniques. One of this technique that we will focus on in this work is the splitting. And let me here briefly introduce what is splitting. So in the classical splitting idea, the state space, so there is a Markov process, and the state space of a Markov process is decomposed into nested subsets so that the rare event is represented as the intersection of decreasing events. Then within each subset, the sample paths of the Markov process are split into multiple copies with the goal of promoting more occurrences of the rare event. However, the classical splitting cannot be applied to our problem because there is no Markov process that we can split here. Actually, the probability of interest is time independent. Then we cannot directly apply the classical splitting approach to compute or to estimate L. So the idea of that we will follow is to try to embed the time independent distribution of interest within a continuous time Markov process. Then we'll see later that this Markov process will have exactly the target distribution at a specified time instant. And with this embedding, we will apply any suitable version of the dynamic splitting algorithm to estimate the quantity L. So two main contributions will be shown in this talk are the following. First, we will see that the proposed estimator is unified and it requires only the quasi-monotonicity and the independence among the random variables. And second, we'll stress on the large scope of applicability of the estimator, and we'll apply our estimator to 4 different problems, which are the CDFs of sums of random variables, CDF of ratios of independent random variables, CDF of partial sums of ordered random variables, and the CDF of weighted sums of independent Poisson random variables. Let's move now to the second part and to show how we modify the classical splitting method in order to be applicable to our setting. So recall that we aim to estimate the quantity L. And as I have mentioned before, there is no underlying Markov process that we can split. So the idea is to embed the density of the random vector X within a continuous time Markov process, X of t and t is positive, in such a way, X at time equal 1 had the same distribution as the random variable, the random vector X. And then giving this embedding, we apply the original splitting idea. So a suitable Markov process for our purpose is the multivariate gamma process. And let me recall what is a gamma process. So it is a process that is equal to 0 at time 0. It is continuous time and continuous state space process. And it satisfies first the increment are stationary and gamma distributed. That is gamma of t plus s minus gamma of t, j of t minus j of t plus s minus j of t have the same distribution as a gamma with shape parameter s, and we choose the scale parameter in this work to be equal to 1. And this is true for t and s strictly positive. Also, we assume that the increment are independent. And the third property is just to ensure that the paths of the gamma process are right continuous with left limits. So this is a univariate gamma process. Next, to define the multivariate gamma process, we let G1 to Gn to be independent gamma process, and we collect them into a single vector J, which is the multivariate gamma process. Okay. Next, this is how, this is a simple algorithm to generate the gamma process. So we start at time zero at 0, and then we simulate the increment independently, and then we do the cumulative sum, and this is repeated from time t1 up to time tl. And in this figure, we plot three paths of the gamma process. Yeah. Next, given the multivariate gamma process, we define the Markov process x of t as given in equation 5. First, when I is in the index set I, we define xi of t to be the inverse CDF of the ith random variable applied to 1 minus exponential of minus gi of t. And when I is in D, it's the inverse of the CDF of the random variable I applied to exponential minus gi of t. So from equation 5 and knowing that j is an increasing, is increasing in time, we deduce that we have almost sure partial, and in fact here we have total ordering of the vector for all s and t. So it means that when I is in the index set I, then xi is increasing in time, and the opposite conclusion is observed when I is in the index set D. Another important consequence of equation 5 is that at time t equal 1, given that gi of 1, we come back here, it is gamma process with shape parameter 1, then it's an exponential. It is an exponential random variable. Then we know that xi of 1 will have the desired distribution with CDF fi of x. This is very important to understand, and this is the same when I is in D. So what we deduce is that the outcome of the original vector x is a snapshot of the state of the constructed Markov process at the time instant t equal 1. So 3 interesting remarks here. First, the embedding process can be any general Levy process instead of the gamma process. However, we choose the gamma process and later we choose the Poisson process because of their simplicity and the availability of many analytical formulas. However, also as a future direction, it's not clear if the algorithm can be improved by switching away from the gamma process to some more complicated generalized Levy process. So, and we leave this as a future direction. So let's continue the presentation of the estimator. So from given that x of t is increasing in time and s is quasi-monotone, then we know that the s of x of t is increasing in time, and the tau gamma defined as the supremum over all possible over time of s of x of t less than gamma exists and unique. So another consequence, if we consider a partition of the interval 0 and 1, the state space can be decomposed into decreasing sequence of event. So S of x at time t0 less than gamma, it will include the S of x at time t1 less than gamma, and etc. Then using this decreasing sequence of event, we can write the quantity of interest L as the product of these conditional probabilities. So any question up to here? I mean, is it clear?
Yes, Nadhir, I have a question. One remark, one question. I visited some talks of our KAUST statisticians, colleagues from KAUST, and they use Pareto distributions and two others, I forgot their names. Can you please comment why not to assume some like Pareto distribution why you go your path?
You mean Pareto distribution to do the embedding instead of the
No, no, to model rare events.
Yeah, I mean, it's possible. I mean, actually, I mean, since I'm, as I mentioned, I'm focused. I focus on application on wireless communication, and Pareto distribution is not very common in that direction. But in statistics, yes, there are applications where the Pareto distribution is considered, and this approach is general. It will not. It will work even with Pareto distribution. What we need here, if I come back, we need independence among the random variables, and we need to know the inverse CDF in a closed form. And for the Pareto, I think the inverse CDF is very simple in this case. I mean, then we can apply it to the Pareto case.
Okay, and my comment, actually you did reference to Monte Carlo method, but I remember I saw many years ago paper of Dongbin Xu. He had kind of multi-fidelity method. So he has some coarse model, fine model, some average, intermediate model. I think it would be kind of interesting that you compare it not with classical Monte Carlo with 10 power 10 samples, but with more advanced techniques.
Yeah, I mean, here the motivation is just to motivate the use of variance reduction technique. This is very like, I mean, you will see later that I will not compare with this, with the Monte Carlo. I will compare with other estimator that are much more better than the naive Monte Carlo. So this is just motivation why we need variance reduction technique and why Monte Carlo fails in the regime of rare event. I mean, just a small motivation. But I agree. I mean, in the comparison, one should compare with something that is efficient, more efficient than Monte Carlo.
Okay, thank you very much.
I will see later that I will, I mean, compare to other efficient estimator. Yeah, thank you. Okay. Now, once we write our probability L as a product of conditional probabilities, and this decomposition suggests that we may estimate the conditional probability here, I mean, appearing in this product sequentially. So the algorithm is summarized as follows. So first, we simulate S numbers of independent version of X at T1. So we start at T0 and X at T0 is 0. And then we evolve the Markov process up to time T1. And we collect all the paths that satisfy this condition. And we collect this path in the set chi1. And obviously an estimate of the first term in this product would be the cardinal of x1 over s. So it's like we use naive Monte Carlo in this from time t0 to time t1. Then what we do, we randomly resample S Markov states from the path that are in chi1, and then each such Markov state evolves for a next period t2 minus t1, and again we collect all the paths that satisfy this condition in the set chi2. And again, we estimate the second conditional probability by the cardinal of x2 over s. And this process is repeated until the final time, final level TL. And then we take the product of all the conditional probability estimate to obtain this final splitting estimator in our case. Is it clear, this algorithm? Any question? Okay. This is to illustrate how the algorithm works. So at time 0, we start at 0, then we run 2 paths here. So S is equal to 2 here. So if the path is less than the threshold, then we split it in 2. Otherwise, for the other one, we don't simulate it, because we know that we don't continue the simulation, because we know that this S of x of t is increasing in time, and this path will end being above the threshold. From T1 to T2, we do the same, and etc. So for this small, and for this very simple case, the estimator is 1 over 8. Let's talk now about some applications that the proposed estimator can handle. The first is the CDF of sums of independent random variable. And as I have mentioned in the beginning, this is very important probability as it serves to compute outage probability in the field of performance analysis of wireless systems. So I mean S of X would be equal to this sum, and X1 to Xn are independent and represent some channel, fading channel amplitude and power of the signal power of the channel and etc. So in most of the case, the CDF of the sum of independent random variable, even if it looks easy, but it's not, the CDF is not known in closed form expression. Some examples are the log normal, the Rayleigh, the Nakagami, and the Rice distributions. And the calculation of L has been extensively investigated in the literature through either approximation methods or efficient simulation techniques. But none of them is generic. And this is one of the features that the splitting method has. So the splitting method is very generic. We do not assume any particular distribution of X1 to Xn. We only assume independence and the existence of the inverse CDF. Here, we'd like to mention that our technique still applies to some class of dependent random variables. For instance, it applies when we have Gaussian copula model, as long as the square root of C of the correlation matrix has positive entries, because if S of X is quasi-monotone, then S of C times X is quasi-monotone also. Another example where we consider this transformation T, and this transformation, we can show easily that it preserves the quasi-monotonicity. So if S of X is monotone, then S of T of X is less than S of T of Y and so on. So with this transformation, we can consider dependent random variables, and we still have the quasi-monotonicity. The second application is the ratio of independent positive random variables. So this is given in equation 12. So again, this serves to compute some outage probability when we have interference. So X1 is the useful signal. This is the signal that the user sent, for instance, to the base station. And X2 to Xn are the interference coming from different sources. And eta is the variance of the additive white Gaussian noise. And this quantity is known as the signal to interference plus noise ratio. So to the best of my knowledge, this quantity have been considered for some distribution like the log normal distribution, for instance, and hence construct a simple generic estimator that works for a wide range of distribution is of practical interest. So the splitting here fits to this problem, and since this S of X is quasi-monotone, and also here I would like to emphasize that we don't assume again any distribution, particular distribution of the random variable X1 to Xn. The third application is the when S of X is given by the partial sum of order statistics. So we order the random variable from X1 bigger than X2 up to Xn, and S of X is the sum of the first of the biggest n bar out of n order statistics. Again, this has a very important application in wireless communication. And the study, of this problem, only few studies exist to study this problem in the literature. So again, S of X is quasi-monotone here, and it is sufficient to embed each of the Xi with a monotone increasing transformation. Again, we do not assume any particular distribution for the random variable Xi. The last application is the weighted sum of Poisson random variable. And we consider the case where n is very large, so that this probability is difficult to compute. So as I have mentioned, X1 to Xn are independent Poisson random variable with rate lambda 1 to lambda n, and the PMF is given in equation 15. And here, in this particular case, we don't need to use the gamma process to embed for the embedding process, since each Xi is by itself have the same distribution of the continuous time Markov jam process, Xi of t. So it's enough to use the Poisson process as embedding to embed the system here. So there is no need to use the gamma process. To the best of my knowledge, there is no Monte Carlo estimator that we can compare with in this setting, where we have weighted sum of Poisson random variable. And what we did is to construct an importance sampling estimator in order to be able to compare it with the splitting one. So let me recall briefly what is importance sampling. So L can be written as expectation of this indicator function, and then we write it as expectation of the same indicator function times the likelihood ratio, where the expectation is with respect to new probability measure that I call here P theta. The likelihood ratio is just the ratio between the underlying probability mass function over the new probability mass function. And the idea here is to propose a new measure that given by scaling the rate of each Poisson random variable x1 to xn by a common factor theta, when with theta is between 0 and 1, and it goes to 0 as gamma goes to 0. It means that the PMF, the new probability mass function, is given by this Poisson PMF with rate lambda I times theta. Then the importance sampling estimator is given by equation 21. So it is a sample average of the indicator function times the likelihood ratio. And here the samples are sampled independently according to this probability mass function. Now, how we choose theta? We choose theta such that the expected value of the sum of Wi times xi under the new measure is equal to gamma. It means that gamma is the mean of this random variable using the new measure. So the event, this rare event, is no more a rare event in the new with the new measure. With a simple through a simple computation, we find theta star to be equal to gamma over the sum of Wi times lambda I. Next, we move to present two heuristics to select the levels, to select the time where the splitting is performed. So the aim here is to provide two heuristics algorithm for selecting good intermediate times T1 to TL-1 and the number of levels at which splitting is applied. So the first heuristic is universally applicable. However, the second applies only to sums of random variable. The criterion, as I said, is to choose the conditional probability appearing in the product to be equal to P bar independent of the level. And this should be true for all L from 1 to L minus 1. And for some fixed P bar, as I have said, and this P bar is chosen to be equal to 0.1 in our numerical results. So the results in these two papers suggest that a reasonable value for P bar lie in the range between 0.1 and 0.5. And in our numerical experiments, we suggest that we suggest a value of P bar equal to 0.1, and this value already gave nice results. So the first heuristic is to run a pilot algorithm to determine an initial guess of L and intermediate splitting times T tilde, and also an estimate of the cumulative of the complementary CDF of the random variable tau gamma. So this is the green dots in this plot. Then we use linear interpolation to approximate the complementary CDF on the whole interval 0.1, and then the splitting levels are approximately given by inverting this estimate of the CDF of the complementary CDF at the point P bar to the power L. These are given by the red dots here in this figure. So this is the first heuristic that we use, and this, as I said, is based on running a pilot algorithm to estimate this red points. The second one is not generally applicable. It applies when the S of X is equal to the sum of Xi. And the idea is to use a closed form analytical lower bound for the probability of interest. So the probability of interest is lower bounded by this quantity, and the time T1 is found by solving this equation by equating this lower bound to P bar. And This lower bound has a closed form of, expression as in equation 26, where gamma is the incomplete gamma function. So once we found T1, then we found Ti by similar procedure by equating a lower bound to P bar to the power I. So this procedure can be easily adjusted to the case of sums of order statistics and to the weighted sum of Poisson random variable. However, for a more complicated choice of S, the first heuristic, which is based on averting the complementary CDF, is preferable. Let's move now to the simulation result. So we define some metrics that will be used to compare the various estimators. The first metric is the relative error, which is the coefficient of variation using M replication of an estimator L hat. So this is equal to the standard deviation over the probability of interest times square root of the number of samples. This metric is up to a multiplicative constant equal to the relative half-width confidence interval resulting from the use of the central limit theorem. So in order to include the computing time in our comparison, we define what we call the work normalized relative variance of an estimator L hat to be the relative error square times the computing time in seconds. So when we compare two estimators, the one with the smaller WNRV is more efficient because first it exhibits smaller relative error for a given computing time, or equivalently, it requires less computing time to achieve a given accuracy. It's important to mention here that this work normalized relative variance is independent of M and depends only on the cost per sample, which is fixed. So to convince you, suppose that Zm bar is the average of M independent and identically distributed random variables, each taking C time to simulate for a total of M times T time. Then the work normalized relative variance is equal to the variance of this estimator over the mean square times total computing time, which is M times C. And then there is a simplification here, M disappear. And finally, we see that the work normalized relative variance does not depend on the choice of M. It depends only on the cost per sample and of course the variance. So this is the first result for the CDF of weighted sums of independent Poisson random variable. We use the second level selection heuristic, which is based on the lower bounds. The number of samples per level is chosen to be 3,000, and the algorithm is repeated 200 times in order to be able to estimate the mean and the variance by sample mean and sample variance. We compare the splitting method to our importance sampling estimator that we derived, and we see that in this setting, the importance sampling is more efficient than the splitting method. This will not exclude this splitting method from being a useful approach, since it is useful to many other applications, not only for the Poisson random variable. The second application is the CDF of sums of ordered random variables. And again, the second heuristic is used to select the levels. The same system parameters are used. And we start with the case where the random variables follow the Weibull distribution. Alpha and eta here are the shape and the scale parameters. So the comparison is made with respect to an importance sampling estimator developed in this paper. Let me just briefly introduce how we constructed the importance sampling estimator in this case. So we define A to be the event, the rare event, the event of interest, and we consider A1 is another set that include here A, not S, so small mistake, with the probability that X in A1 is known. Then we can write the probability of interest as the product of two probabilities, which is the probability of X in A1, which is known in this case, times the probability, the conditional probability of X in A given X in A1, which is when A1 is close to A, it's not a rare event probability. Then we can use Monte Carlo to estimate this one. So we may write this estimator as expectation of L1 times an indicator function, and X in this case is the truncation of the underlying PDF over A1, and L1 is the probability of X in A1. The straightforward computation of the variance of the new estimator is given by L1 times L minus L square. And we clearly see that whenever L1 is close to L, then the variance would be small. And when L1 is equal to L, we get the zero variance measure. So our choice of A1 is to consider the maximum. This X1 is the maximum among all other random variables, all other variables. And L1 is given by the probability of X1 less than gamma to the power n. And the efficiency of this estimator is proven in this paper. So for distribution satisfying this equation, we prove that we have what we call the bounded relative error. It means that the coefficient of variation is bounded independently of how small is the value of gamma. This means that we need a bounded number of samples to meet a fixed accuracy requirement, and this is independent of how small the rare event is. And this is one of the most desired property in the context of rare event simulation. So this is why we, in the example of a viable distribution, so the viable distribution satisfies this property. This is why we see that the universal importance sampling, it's more efficient than the splitting algorithm. This is because we have the bounded relative error in this case. However, when we move to the log normal case and we use the same system parameters, we see that the splitting method becomes more efficient than this importance sampling estimator. And the efficiency is almost 10 times here. Next, we move to the ratio of independent positive random variable. We use now the first heuristic based on this inverse complementary CDF. S is equal to 3000 and M is 200. And the comparison is made with respect to the variance scaling importance sampling estimator in this paper. Let me first review how we constructed this estimator. First, we consider yi to be so in this case, we consider the log normal distribution, and yi would be Gaussian in this case, with parameter mu I and standard deviation sigma I. And then the probability of interest can be written as the probability that a sum of correlated log normal is bigger than 1 over gamma, where Z here is a multivariate Gaussian distribution with mean and sigma that are given by these two expressions. The idea that we proposed in this paper is to scale the covariance matrix by the factor 1 minus theta, where theta will go to 1 as the event is rare and rare. So the value of theta that we choose is basically to minimize an asymptotic expression of the second moment of the importance sampling estimator. And for more details, this paper is available. You can have a look. So a comparison here, so it shows that the splitting method is more efficient than this variance scaling importance sampling scheme, and we have almost it's almost 5 times more efficient here. So to conclude, we proposed a dynamic multi-level splitting estimator to efficiently evaluate various time-independent rare event problems. The idea is to embed the time-independent problem within a continuous time Markov process so that the distribution of interest corresponds to a snapshot of the Markov process at some time instant. Then what we did is to apply a version of the classical multi-level splitting to construct our estimator. The main feature of the proposed estimator is its wide scope of applicability, as illustrated in our examples of estimating various wireless communication performance metrics. And numerical results show that this estimator compares favorably with existing estimators. As to possible future direction, we'll try to reduce the complexity when n is large. And the idea is we can try to introduce some hierarchy with respect to n in addition to the hierarchy in time. Also, another possible direction is to apply the approach to other applications such as financial engineering and economic system in addition to this application in wireless communication. These are the references that I have used. And if you have questions, please